So before I continue with our review, does anyone want to bring up any questions about the material so far or about assignment 2?
Yeah, I have a quick question. Does
Sure.
it, since I know we're checking for like plausible solutions lower down in the code, does it make sense to print a board theoretically that wouldn't work? Or should we like make it so it prints like an error message or something like that? Like, let's say like the input is like 122 or something. It's like a list. Like, does it make sense to just print that out? Or does it make sense to not print that out?
You mean like where 122 is like a list of possible board sizes or something like that, instead of just like an integer?
It's like that's like the input, which if you check the plausibility of the code later on, it wouldn't be a possible one. So should we kind of have something in our code higher up, where it makes the actual board print out? Should we have a thing that says, oh, this is not a plausible board? Or should we just print out any possibility that's put in there and then have it just tell you later on that that's not possible?
So you're talking about the check solution function?
I am talking about, sorry, let me check the name of it really quickly. The part where you're basically like appending to the board and printing it out. So like you're defining like row to string and then it does a little asterisk and all of that. Like I'm just basically saying, does it make sense to allow that to basically print out any input, or should we kind of have something in there where the input, if it's not plausible, it shouldn't print it out?
Yeah, that's a great question. So I'm not going to give your board to string function bad inputs. So I won't give you repeated elements.
Gotcha.
That would be interesting, but maybe I'll do that in future years. But I did not set up the test that way for you all. So you can assume that the board is going to be like a unique permutation of the integers 1 through n-1, where n is the board size.
Thank you.
The one thing you should, let's see. One thing you do have to check for is that in the is solved function, it is possible. So the no repeats applies to the board to string function. So you don't have to make that super complicated. However, in the is solved function, the like unique rows, that line there. So like the first block of code you have to fill in, that you do have to check specifically for repeats. So like that's how you solve that line. So you may have repeats there.
I wasn't sure if we should still be thinking about that higher up or not, which is why I was wondering. Thank you.
Got it. Higher up being the
like
print out the board.
The printing part. Mm-hmm.
Got it. Yes. You don't have to think about that until the is solved function. Any other questions?
I had a quick question about the public rubric.
Sure.
It could be incorrect, but the answer that I was expecting for the second board to string test is different than what I would have thought, just based on the numbers. I'm not sure if I'm missing something, if anyone can see that, but.
Do you want to share your screen and we can walk through it?
I'm mostly just looking at the public rubric right now. I can share my screen, but it's just the public rubric.
Okay. Well, it's up to you, I guess. Sure. Whatever you'd like.
Happy to. Let me switch over to this. So for the second board to string question, I would anticipate, so this first argument looks good, that the queen is in space 0. This second one, 0, 1, 2, 3, 4, I would expect it here. And it looks like it's in 6, correct, for the solution that's expected. And then 7 here for this one is incorrect. So there's a different solution that I would expect based on, or a different input that I would expect based on
So I'm guessing you may be thinking of the transpose of the notation in transpose. So the way the boards are represented here, so it doesn't affect the is solved function, because if the board as it's set up is a solution, then like flipping it by 90 degrees will also be a valid solution. But for the print, the board to string function, it will matter. So the positions of each element reflect the column number, and then the value in that column reflects the row. So when it says like 0 for the first column, that means the first, like the position, the 0th element, which is the first element, corresponds to the column, and then the value there corresponds to the row. So the 0th row, or the first row of the 0th column, or the first column, and then the 6th there corresponds to the row that contains a queen in, or sorry, the column that contains, so column 1, row 5 will contain a queen. So it's not that there's a queen on the 5th row, 2nd column, which is, I think, what you're maybe interpreting it as.
Okay, I'll take a closer look at that.
Sorry, I'm not sure if I just said that backwards. Let me say it again. The positions correspond to the columns, and the values correspond to the rows, in case I said it backwards.
Okay, great, thank you.
Yep. So the samples, so like the sample printouts in the notebook are correct, if you count them. I mean, I can, yeah. I'm just checking them over now. Yep. Yeah, they look correct to me. Okay. Well, sounds like I am never short of bread. That is true. We bake a lot of bread in this house. Okay, any other questions? Yes.
Yeah, I was wondering if you could just, so like your recommendations for the, like the is solved thing where you're like actually checking for the diagonal solutions, like the actual like sort of algorithm makes sense to me, but I'm just sort of don't like the NP functions. Like, could you just like explain?
What do you mean NP?
Like the numpy arrange and numpy unique. I think I get you what unique does, but could you just like talk through very briefly what those do? Like the actual like on website thing, the descriptions are like really weird. It's like the
why don't I share my screen and we'll explore those. That's cool. That's a great question. Okay, let me get your smiling faces back. Okay. Okay, so we'll import the NumPy library. Yeah, so one way to check is just to call them in like a Scratch notebook like this. So arange acts kind of like the range operator. So it gives you like, well, let's see how the range operator. So the range operator, it gives you an iterator. Again, we haven't, sorry. We have not learned what an iterator is formally yet, but we will in a few minutes, hopefully. But if you convert range, which is an iterator, to a list, it creates a list with the elements 0 through 1 minus this number, giving you a total of this number of elements. So in this case, 0 through 9, incrementing by 1. The NumPy function arange, the A stands for like array. And so it creates kind of the same thing, but as a NumPy array object, which is like the NumPy version of a list. And then does that make sense? So you can treat it just like the range function, but it produces an array. But you can like loop through it just like a regular range or list or whatever. So it's a Python iterable also. And then the second thing you asked about was the unique function. And that just gives you the unique elements in a array or list. So just to see how that works. Oh, it also sorts them. Let's see, so. Okay. So this will like remove any repeats. And if we had sorted them, if they weren't sorted, they would be sorted at the end. And then the thing you pass in could be an array or not. So if you take a list and turn it into a NumPy array, you can pass that into the unique function also.
Okay, that makes sense.
Sure.
Just one other question, actually two. Just briefly for the is solved function, in the rubric you have, I think it's 1 and then 0 for the correct outputs, but the code says true and false. I just want to make sure that that will sort of produce, that won't bother the grader.
Yeah, so true equals 1 evaluates to true.
Okay.
And then that
great.
evaluates to true also.
And then the other question, I think somebody brought this up in a chat earlier this week, just to make sure so the rubric has sort of a pair of double brackets on both sides of the variable pause. Is it going to be bothered by having, like, are you going to put it in with double brackets? So should we be extracting that list in our code, or do we just assume that it's a...
So that's a great question. Yeah, so what it's actually doing, what the auto grader is doing, is it's saying, so let's say you have, like your argument is like 9, if that's what's listed in the notebook. What's actually happening there is, let's write some function, like, I don't know, let's make it square the number. Okay, so what the auto grader does is it says, it calls the function that's in the func column, and then it calls it with star, and then whatever's in the args column. And what that does is, if you have like a list of elements, it'll be as if you passed in each item in the list as a separate argument, but it like allows, but it's functionally equivalent to passing in square of 9. So this,
Okay.
Let's, yeah, so, so like if we did this, we could say like, oops, sorry. So this is equivalent to exponent of 9, 2. These both mean the same thing, these lines here.
Mm-hmm.
And then we haven't really used named arguments, keyword arguments, but the KW args column in that takes in a dictionary. So if you pass in a so like if you had a named argument, then you could do something like this. And then that would be equivalent to this. So this is a dictionary whose keys are the names of the arguments and whose values are the values that you pass to those arguments.
Okay.
And the star, the single star means unpack a list, and a double star means unpack a dictionary.
Okay.
It's just a Python thing that is occasionally useful. Okay.
Thanks.
Yeah, these are great questions. Sure. I think if you want to check out the auto grader code, just if you're curious, it's in the auto grader, like in the assignments folder, in the auto grader folder of that. So like if you wanted to, you could dig into actually how it works and all that.
Thanks.
Possibly of interest. Okay, any other questions? All right. Okay, so on Wednesday, let me clean this up. Okay, and I'll reset the runtime, just I like to do that. Okay, so yeah, so on Wednesday, we ended class by talking about list comprehensions. And that was like our first real exposure to like some uniquely Pythonic syntax. And if you want to dig more into those ideas, Python also has a similar syntax for creating dictionaries and sets, and that's called like dictionary comprehensions and set comprehensions, respectively. So I don't want to take too much time going over them in detail because they're very similar to list comprehensions, but I can maybe provide a quick example, and then also like tutorials are readily available if you ask Google. But here is how you make a dictionary comprehension. So I'll do like a few examples. We'll make a dictionary of the squared element. I don't know why I'm thinking about squares today, but okay. There we go. So that'll make a dictionary whose keys are the integers 0 through 9, and whose values are after the colon are the squares of those numbers. So x1 of 4 will be, the square of 4, which is 16. And then like the keys can be anything. Usually they're strings. And so this would turn them into strings. And now this won't work, but this will. Okay. And then similarly, a set comprehension looks almost exactly like a list comprehension, but you just replace the square brackets with curly brackets. So like, yeah, so suppose you wanted to create, why not, a list of the squares of the numbers 1 through 10. This is how you do it as a list comprehension, or one way to do it as a list comprehension. Okay, so that works like we thought. But if I wanted to make this a set comprehension, I just literally just replace the square brackets with curly brackets, curly braces. That makes it a set. And then you can see that it's not like a normal list. if I make a list with like some repeats in it. So it'll go through all these things, but in the final set that gets created, it can only contain unique elements. Okay. All right, any questions about that? All right. Yeah, and so set comprehensions and dictionary comprehensions also both support the like if else strangeness that list comprehensions support, and the syntax is the same. So okay. Another quick note I wanted to mention from Wednesday's class is that I think it was Brian brought up a Python construct called a decorator. And I said that I didn't have a tutorial for decorators in this course, but after thinking about it more, I decided that some of you might find it interesting to learn about decorators. So I've added a new tutorial on decorators to the module 3 material that you can check out. And then, like, in addition to pointing you to that new content, I also wanted to like remind you that your questions and comments that you bring up in class like actually have an effect on the course. So I have an agenda in mind for this class, which I'm like dutifully ticking through. But what we ultimately learn and discuss isn't like a static, unchanging thing. It's actually causally related to stuff you say during class or like otherwise communicate to me. So anyways, food for thought. Okay. So next, in that spirit, yeah. Sorry.
Just for sorry to go back here. I just
Yeah.
was peeking at the public rubric again for assignment 2, but I apologize if it was mentioned. But the third item, it looks like the one of the brackets is the wrong way on the public rubric.
Okay, let me pull it up.
It's for the
sorry.
third one.
Yeah. So this is okay. Public rubric. You probably can't see what's on my screen because I'm not sharing the full thing. But third item is solved. Ooh. Yep. That's going the wrong way. All right. It's not going the wrong way anymore. I fixed it. Thank you. Okay. So just to, yeah, thanks for mentioning that. In case, well, as I mentioned, like, you know, the auto grader is useful and all that. I run my own, like I do the assignments myself before I assign them to you. And I run my own code through the auto grader. So like, if I don't get 100 on it, then that tells me that you might not get 100 on it. And then I look into that issue. And so so like if everyone got question 3 wrong, that would trigger a flag for me. But good to directly raise it also. That was definitely a typo though. Okay. Yeah, so in the spirit of bringing up things that you care about, next I want to tell you about 2 other Pythonic constructs that none of you asked about or indicated you cared about. So these are called generators and iterators. Okay. I actually do think they're useful and interesting. Hopefully you will also. Okay, so suppose that you wanted to do some sort of calculation where you're like working with the set of all non-negative integers. So like infinitely many things. So you couldn't store that set in memory because you can't store infinitely many things really anywhere. So that's tough. And then, or like suppose you wanted to apply some like long running analysis to your data set, but only if some sort of set of conditions were satisfied later on in your code that you don't necessarily know about right at the beginning. So you can do those sorts of things using constructs in Python that are called generators. Sorry. Okay. So generators are a way of carrying out what's called lazy evaluation. And the idea of lazy evaluation is that computations are only carried out at the moment they're needed. And until that moment, the computer only needs a record of the work that it might eventually need to do, but it doesn't actually do that work. So yeah, so let's make our first generator. So one way to make a generator is to use a format that's also similar to list comprehensions, but we can just replace the square brackets with parentheses, rounded brackets. So this is called a generator comprehension. So yeah, so we could do my favorite thing, square the numbers 0 through 10. So now, so in a list comprehension, that would actually contain the answers, but y is now a generator object, not a list. Okay. So to get the values of y, you have to use the next keyword in Python. So like next y, the first time you call it, evaluates the first item in the list. And then if I evaluate the same thing again, gets me the second item of that generator, and so on. Okay. Does that make sense?
How would you call like a certain element? Like if you wanted to call like 8, you wouldn't like, would you have to iterate through all of them?
Yes, you cannot call, yeah, so let's try that. Yeah, it's not subscriptable. You can't do that. And that's important. So you could have a generator, maybe we could do an example of this, where generating the next item in the sequence depends on calculations from the previous number in the sequence. In order to get to the 8th thing, you'd have to compute 0 through 7 anyway. So you're totally within your Pythonic rights to call next 7 times and throw out all those answers and then only do something with the 8th one. But if you're using a generator, you can't, like there's no shortcut for having Python do that for you. Okay. So to see the difference between generators and list comprehensions, let's create a new square function. I'll call it chatty square. And it's going to do the same thing as square. So it's going to raise x to the power of 2. But then it's going to print out the thing, like the answer. So oops, there we go. Okay, so so it prints out 6 squared, the thing I passed in squared, equals, and then the actual answer, 36. And then it returns 36. Okay, so if I use chatty square in a list comprehension, then y1 will contain the squares from 0 through 9, just like it has in all of our other examples. But you can see that chatty square has now been called like at the same time I assign this variable y1. And we can tell that it's been called because all these things have been printed out. But suppose I turn this into a generator by making these parentheses. Okay, so I evaluated this function and nothing happens. No, nothing was printed out. And y2 is not a list, it's a generator. But then if I call next, then it's going to just evaluate the first, like it's going to square just the first element. And if I call it again, it's just going to do this, the second element and then return it. Okay. And then I could like finish it off by, yeah, so when I get to the end of the sequence, it's going to throw an error. So like I can just loop through everything by wrapping the next command in a try except statement. And then once I get an error, I'm going to break out, and that'll call the next command until I reach the end of that sequence, and then it will break out of the while loop. Does that make sense? So that the chatty square function is called at the time the statement is evaluated. Or sorry, in the list comprehension version, the chatty square function is called at the time the statement is evaluated, this original statement. So like when y1 is assigned this list. But in the generator comprehension version, the chatty square function is called lazily only at the moment that the next value of the sequence needs to be computed. And then when it's needed, it's only called for that one next value. So it's worth thinking about how this idea of lazy evaluation might come in handy. So like, let's say you're running an experiment where timing is really important, like, you know, real-time feedback setup, where like you need to ensure that some stimulus presentation or measurement starts right at one particular moment. And then like, let's also imagine you want to generate stimuli on the fly, and like it takes a little time to generate each stimulus. So you might want to do some sort of setup when the experiment starts by like defining a generator object that gets created nearly instantaneously without doing any computations. But then only when you need each individual stimulus in turn, you could generate it right when you need it by using this next keyword. Does that make sense? Okay. And then you could also encounter some situation where you don't necessarily have all the critical information you need when the generator is created. So we could write like a twist on this chatty square function. So we could raise, let's see, so I'll define this variable exponent, and then chatty power is going to raise x to the current value of exponent. And then, oops. And we'll return y. Okay. So yeah, so now we have this exponent variable that's defined outside of the function, and we'll explore more what that means soon when we talk about variable scope. But for now, all you need to know is that like this is a valid Python program, and the value of exponent that is set outside of the body of chatty power here, it can be referenced from within the chatty power function. And then changing the value of exponent will change the behavior of chatty power, even though neither the body of the function nor the arguments that we passed into the function changed. So that can be tricky. Okay, so if we were going to write like a list comprehension, let me clean this up, that depends on chatty power, then every item in the list is going to be evaluated using the same exponent, like which is whatever its value is at the time we create the list comprehension. So let's do that to demonstrate. Chatty power of x for x in range 10. Okay. So they're all 2. Okay. But if we use a generator, then because every item is computed lazily, Python will reference the value of exponent at the time each item is computed, which could potentially change across items. So for example, let's do a generator version of this. Oh gosh. Now you know where my brackets in the wrong way came from. Okay, so there we go. So that's a valid Python expression. So I could do like next of y3, and that evaluates with, the exponent is just 2. But then suppose I change exponent to 3. Now I'm going to start raising things to the 3rd power. And then I could change it to 10 and start raising things to the 10th power, etc. Okay. So you could think about how that might be useful. Okay. So in addition to generator comprehensions, another way to create generators is by writing a generator function. So generator functions look like regular functions, but you like replace the return keyword with a new Python keyword called yield. And then whereas like generator comprehensions need to use like this squashed for loop syntax that's analogous to list comprehensions. Generator functions can use while loops, so they could potentially be infinite. Let's clean that up. So like that example I gave where you like store all the non-negative integers. Let's make a generator that does that. So we'll start with 0, and then while true. So normally that's like a no-no because that would be an infinite loop. But we're just going to yield. We're going to return the value of I in whatever it currently is, and then we'll increment it. And that's our whole function. Let's then we could like print out however many integers we wanted. This will be, yeah. So if you add this end keyword object to a print statement, instead of printing a new line at the end of the print statement, it'll just print a space. So that'll make our results a little more compact. So, and then we could like keep doing this, and that'll start with 20 and continue on. And we could do that as many times as we want. So we are storing a variable in memory, ints, that contains infinitely many things, but we can easily manipulate it and work with it, just as if it were any other type of list. Okay. And then let's see. Okay, let's make another function. This is like a classic one. We could write, does everyone know like the Fibonacci sequence? So this is like a classic computer science thing. So, it's a mathematical thing, but so in a Fibonacci sequence, you start with 0 and 1, and then every subsequent number is the sum of the previous 2 elements. Okay. So we could write a generator object to generate an infinitely long Fibonacci sequence. So we could like store, here's the number 2 numbers ago. Just to make it easy, we'll start after the 0 and 1. Otherwise, we have to write a special case for that. And then while true, we're going to yield 1 back plus 2 back. And then we have to update 1 back and 2 back. So, actually, there's a trick here. So here's a naive way of doing this. We could just set 2 back equals, this won't work, but we will explore why. Okay. So if I did this, does anyone know why this isn't okay? I don't know if it's too subtle.
Will it then update 2 back to be the same as 1 back? Like sort of go backwards and do that?
Can you be more specific? You might have it. I can't tell though. Can you be a little more, can you like unpack that a little more?
Yeah, because 2 back is assigned to 1 back. So if you change the value that 1 back has, then it will then change the value that 2 back has.
Okay, that's a great guess. That's not true. Yeah, so we'll talk about like how Python works under the hood to deal with variable assignment, and that's related to that question. So that's a great guess. That's not the case. Does anyone else have a guess?
Wouldn't this just set 1 back to be, or it would, so you're assigning 2 back to equal 1 back, and then you're assigning 1 back to equal 1 back plus 2 back, but 2 back already equals 1 back. So that makes 1 back just double 1 back.
Exactly.
Adding.
Yeah, so Python doesn't care what you were trying to do. It just does dutifully whatever dumb thing you asked it to do. So the value of 2 back is now what you used to call 1 back. So this actually doesn't mean what the variable name implies. So the right way to do this is like you have a temporary variable that saves the value of 2 back. And then instead of adding the updated value of 2 back, which is now 1 back, you call it temp. Okay, so that I hope will work. So you can make a generator, and then so we're skipping over 0 and 1. So the first value should be 1, and then 1 plus 1, I believe, is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, etc. Okay, so that's an infinite sequence of Fibonacci's. Okay, and then we could do our same while loop trick. Well, actually, if we did our while loop trick, it would just print forever. Because it's an infinite sequence, but we could print out like 30 Fibonacci numbers. And totally happy to do that. We could have picked anything. Okay. Okay, so the way that we're able to deal with these infinite sequences is that the elements of these sequences are evaluated lazily. And so you don't need infinite memory to store them or infinite time to compute them. And then it's also worth understanding exactly when different parts of the generator function are called. So we could modify these functions to say, like when we're starting, and then right before we yield, and then where we increment. Okay. You know, I shouldn't have deleted whatever. Okay. Okay. So nothing happened when I created this generator. When I call it the function for the first time, what's going to happen is the function is going to execute up to the yield statement and then return that value. So it should, so let's see what happens. Okay, so we printed out starting, so this executed, and this function executed up to here, and then it returned the first value, which is 0, and that's why I get it here. But then the next time I call next, it's gonna continue on after it left off, after the yield statement, and then just continue executing. And so because we're in a while loop, we get this incrementing line printed out. So the increment actually happens only the next time I call this function. Okay. So like to summarize that in case, just to make it succinct. So when you call next for the first time, the function is evaluated up to the yield statement, and then the yielded value is returned. And then the next time you call the next function, the function continues its evaluation, picking up after the yield statement and continuing until the next yield statement, which could be the same line if it's in a loop. So the generator is remembering the state where its execution left off when its generator function was last called. Okay. So that's the trick, like the secret sauce that's hiding inside generators that allows them to work. Yeah, Chris, did you have a question?
Yeah, could you sort of use this to like run step by step through a script then, if you just had like yield statements throughout it? So if you wanted to run just this first chunk, then the second chunk.
That's a great, yeah, that's a great idea. There's a type of debugger called a step debugger that basically does that. So if you wanted to write a debug function, you could go in and replace, it's a little trickier than this, because if you're like debugging a generator, you couldn't, like it would have no yield to replace. But yeah, you could write like a kind of simple debugger that doesn't cover all the cases by like taking your program, replacing every function with a generator function by like find and replacing return with yields. That's a cool idea. Yeah, and that could be an interesting way of debugging your code too in these notebooks. Okay.
Cool. Thanks.
Yeah. Any other questions about generators? Okay. So generators are descendants of a broader class of Python object called iterators. And at their core, iterators are a way for Python to produce sequences whose elements are evaluated lazily. And you can make any class into an iterator by adding the next, and cat wants to scratch my chair. Not okay, not okay. Okay, the next method, and that's called when a new element is needed, and it returns the next value in the sequence. And then if the sequence is finite, the next method should raise a stop iteration signal. So that's the like error, let me, so raise stop iteration. So that's like the error that gets called when a generator like runs out of things. And then the next function an iterator needs is called iter. That gets called when the iterator is initialized. and it returns an object, like its only requirement is it returns an object with a next method. Okay, so let's do an example. Okay, so all right. So we'll write something that's going to like count in increments of m, some integer, and let's say it's going to only, yeah, so it's going to like count n things in increments of m. Okay, so this is just like any other class. So we're going to save these variables. Okay, oops. And then we have to make it an iterable by adding next and iter methods. Let's see. Let's have I be the next, like the number of things we've gotten to, and then j is going to be like the value of the thing to return. Or sorry. And then we'll return self. Okay. And then to generate the next object in the sequence, first we have to check like, is self.i greater than or equal to self.n? So have we already gone through n things? If so, we're going to raise this error. Otherwise, we're going to, this is like a trick. This is like the same trick as saving a temporary variable. So we need the current value of self.j. Then we're going to change self.j by incrementing it by our counter amount, and then self.i plus equals 1, and then we'll return the current value. Okay. Does that make sense? Okay, so let's like do some examples. Like if we wanted like 20 elements counted by 2s, we could like use that. And then if we wanted 10 elements counted by 3s, we could do that. And then you could like print out the elements just like any other list. Oops. Okay, so that's 20 things counting by 2. And then uh, 10 things counting by 3. So you can treat iterables just like lists when you're writing for loops. And then each time you use those objects in a for loop, the iterator is going to be reset. So it'll count through the same sequence each time. So if I run this again, it'll count through the same sequence. So you can really treat them just like lists. And that's how that range function works. So iterators can be really powerful when you're working with sequences of indefinite length. And there's also a really useful library that comes as part of the Python standard library called iterators, like that. And you can check that out for some like more advanced uses of iterators that gives them even more power. And then it's also worth noting that just like adding the iter and next methods to a class turns it into an iterable, there are lots of other special methods that you can add to classes to add support for different Python operations. So for example, You can make an object be able to be turned into a string or like indexable using square bracket notation, or callable like a function, or able to be added together or subtracted or multiplied or divided or like manipulated or compared with any other Python operator. And that includes in place operators like plus and minus and, et cetera. And so to get the full list, you can just search for Python special methods, and to like orient you when you get the results back, all of the special methods start and end with double underscores. Okay. Oh yeah.
So I just had a question sort of about the difference between the init function and the iter function. And as I understand it, let's just say you just have a class that just has the init function, and I call it, it's going to return to me an instance of that class, like an object there. But with the iter function, I'm trying to understand when, so obviously it gets called once at the beginning when you iterate there, but couldn't technically like you put the iter code in the init function, because the init returns that instance of an object, and when you create the class, shouldn't that just be initializing the iterator? I'm having a little trouble understanding why they're separated and not together.
So the quick answer is that if you want to use an iterator like this, like we haven't reinitialized this variable here every time we run through this loop. So if I run this loop, it doesn't have to reinitialize that function. It just calls the iter function.
Oh, so is it calling iter each time it runs for
each time? Yeah, each time you want to treat that instance of a class as a like list-like object, it calls the iter function. And that can happen after you've already initialized the object, which you do with the init function. So like another way to kind of, well, I don't know if that makes sense, then that's fine. Otherwise, another way to look at this is by like printing out when different things happen, in case that's useful. So you could say like nexting, oops.
Oh, okay, I think so for example, when you're going through the for loop, it's not calling on each iteration of the for loop, it's not calling iter again. But if you were to create another for loop with it, when it runs that for loop, it would run iter, and then on each iteration, it's calling next. Is that
exactly? Yeah.
Okay, and so the init only gets called the initial time. Iter gets called whenever you go to like run through the whole thing, and next gets called on each run through that loop. Okay, I got it.
That's right. So here's the like printout. So
okay,
it initializes when you, well, here, let me just remove this one. Yeah, so it initializes when you call it the first time. Nothing's getting, the iterator is not getting initialized, and nothing happens with next. Then when you use it in a loop, now this iter function gets called, but only for the first loop. And then each time you get into the loop and it has to evaluate the next element, the next function gets called. Then it returns the next thing and continues on.
All right, perfect, thank you.
Sure. Okay. So since we're, so the last big set of concepts that you need to know about Python is like about how variables are treated. And that's an important thing to understand. We have 3 minutes left in class, and that is not, it's sadly not enough time to go through that. And I want to like take the time to unpack that sufficiently. So let's go over that last part of module 2 on Monday. Yeah, and I So nothing to do this weekend except for finishing up assignment 2 by midnight tonight. If you want to get a head start, next week we're going to start module 3, and that's going to give us like a taste of the more classic computer science concepts like sorting and data structures, just so you like get a little exposure to those ideas. So, you know, if you want to start going through that material, there's quite a bit of it. You could do that over the weekend, but we will hopefully officially finish off module 2 on Monday. Okay. Yeah, so have a great weekend and see you in